Alrighty. Good evening, everybody. Welcome to the Horological Society of New York June 2025 lecture. My name is Carolina Navarro. I'm the Deputy Director, and it's my pleasure to welcome you this evening for a great lecture. So here are a few announcements before we get started. June and July classes are now live, so you can plan your summer accordingly. We're also offering weekend classes upstairs in 506, and we're also taking our courses to Silicon Valley, June 20th to 22nd, as well as Las Vegas, September 13th through 14th. So if you know anyone in those areas, please feel free to let them know. A reminder that we have an amazing exhibit on display on early American pocket watches. It's upstairs as well in room 501. And it includes over 40 magnificent watches made right here on American soil, including the first known pocket watch made in NYC in 1715. The print catalog is available for purchase, which you can see here, and we also have a digital one available on our website for everybody to browse. Okay, and there's still time to shop for Father's Day. You can give Dad the gift of horology with an HSNY membership. We have classes, we have a fine fragrance, and a lot of leather goods. So you can check out our website and do some last-minute shopping. There's always time. And last but not least, a friendly reminder that our lectures pause every summer. So we're not going to have a lecture in July and August, but we will have our library open as well as our classes are going to be taking place. You can always check out our additional lectures, previous lectures on our YouTube video, and we have our summer survey coming soon, so keep an eye out for that. Okay, now for tonight's lecture. So it's a privilege to introduce tonight's lecturer, who oversaw one of the most ambitious clock restorations and conservations projects in recent history. Keith Scobie-Youngs is co-founder of the Cumbria Clock Company and has decades of experience preserving some of the UK's most iconic timepieces. Tonight, he takes us behind the scenes of this remarkable project of one of the most recognized clocks in the world. Please join me in welcoming my friend Keith Scobie-Youngs.
Thank you very much. I'll have it. Where's the clicker?
Right here.
All right, cool. Hello. Thank you very much. It's a great privilege to be asked to come to New York and give a lecture here at the HSNY about the conservation of the great clock of Westminster, better known as Big Ben. Now, just for the records, I know we all know Big Ben is the bell, but everybody knows that the clock is Big Ben. All the tourists who get out of Westminster Tube Station aren't there to look at a bell. They're there to look at a clock tower. So just to give you a bit of inside information, or just a little bit of a warm-up, the conservation of the great clock started in 2017. And from 2017 to 2022, the tower was shrouded in scaffolding. I feel very sorry for the people who made the journey to go and see it, but that's the way it was. The whole project really started because the clock mechanism was starting to be a little bit unreliable. It wasn't being as accurate that we knew it could be. And so we kind of were looking into the reasons why that was. We then realized that it needed a scaffold to overcome those problems. And once you're going to put up a scaffold that size, 330 feet, you might as well do the work on the rest of the tower. So at that time, they got together a whole group of craftspeople, from cast iron specialists to painters to gilders to stained glass specialists to horologists, and also just the joiners, the plumbers and the sparkies to do the work on the tower. And that allowed us to give the clock tower the biggest amount of work of conservation that it's ever had since it was built in 1859. So let's start with a picture of the great clock as it was before the restoration started. It's a wonderful machine. It's about the same size as a large pickup truck, and the mechanism on its own weighs about 5.5 tons. It was designed by a chap called Edmund Denison, later to become Lord Grimthorpe, and built by Edward and Frederick Dent in 1854, and fixed in this position in 1859. And when it was put into the tower, it was the cutting edge of turret clock horology. It really was. It had to drive 4 dials 22.5 feet in diameter, with a minute hand and hour hand. They were the biggest dials in the world at the time with a minute and hour hand. It had to strike a bell weighing 13.5 tons, and it had to be accurate to 1 second, within 1 second of the hour, which is a big ask in 1859. So, with the clock as it was, showing its age, I mean, when I first went to London as a young 20-year-old clockmaker, this clock wasn't allowed to stop. And if it did stop, they had to get it up and running within a few hours. So any repairs were done quickly. And it was those type of repairs which were starting to kind of show their age. And it wasn't the craftsmen who were doing it, the clockmakers who were doing it then, they were bad clockmakers. They just weren't given the time to do it. So it became an opportune moment to do this work. So where do you start when you've got to take out 5.5 tons of clock mechanism? Well, you start with taking the hands off. And the hands had been taken off in about 1980, and we knew that had a great problem getting the hands off. And in fact, they put the hands back on in the wrong order, and then had great difficulty taking them off again. But so we made a puller to kind of take the hands off, which was really useful because it was needed to kind of break that seal. They weren't held in place through corrosion. It was just top quality Victorian engineering, which was making it such a hard job to get them off. But once you got them moving, you could get them off. We learned to get all 4 sets off, get them round the dial, round the tower, and this is a photograph of us holding one of the hour hands. There's me on the end looking pretty grumpy, and then you've got Hugh from the Palace Clock team, Paul and Ian. And they're the people who are at the Palace of Westminster all the time, looking after over 2,000 clocks within the Palace of Westminster, as well as the day-to-day running of Big Ben. The hour hand there is made from bronze. It weighs about 160 pounds. The minute hand weighs about 220 pounds. They're not as heavy as you think. They're actually the 3rd set of hands which went onto the clock mechanism. The first set were made from cast iron. They proved to be a little bit heavy, especially the minute hand, and that was causing all sorts of problems with the escapement tripping through. So they replaced them with bronze. They still had the same problem, so they cut the end off the minute hand, replaced that with a copper cylinder, and lo and behold, that solved that problem. This hour hand is one of the bronze hands from that second set. So we took those off, and then that meant we could start to look at dismantling the dial motion works. These are the 12-to-1 reduction gears behind the hands for the minute, behind the dials for the minute and hour hand, and we're just taking out the minute rod there. It is 8.5 feet long, weighs 160 pounds, and is 3.5 inches in diameter. It's pretty chunky, but it's small fry compared to the hour pipe, which comes in at 360 pounds. And 2 massive counterweights, which also proved a little bit awkward to get off. And you can most likely see now that my world of horology is a million miles away from that of watchmaking. Now, one of the things with this whole project was that the clock or the Parliament wanted one dial showing the correct time all the way through the whole project. So seeing though we've got rid of the hands, we've taken the hands off, we've taken the motion works out, this meant we had to make a replica set of hands. So these are the minute hand and hour hand that we made in the workshops to replicate the originals. And so I wanted to make them so they looked as near to the originals as possible. These aren't made in bronze, these are just made out of steel. They're only needed for a couple of years, so we won't go to that expense. But I wanted that attention to detail, so when people came to London, that when they did look up at that tower with the scaffolding all the way around it, it did look like the original hands are on. The thing is, they needed a movement to drive them with, and so therefore we had to design a big synchronous electric motor which could be clamped in position, which sat between the clock room and the dial, couldn't have those internal counterweights, so we had to put the counterweights on the hands. And so this is one of the units we came up with. Now, during the project, there would have been a stage when one of the newly restored dials, painted in the original Fusion blue that he wanted right at the beginning, would be opened up to display, and then one of the old black dials would be waiting to be covered up. So this meant we had to make 2 sets of hands and 2 movements, and this photograph could only be taken for a 24-hour period as the new one appeared and the old one disappeared. And this photograph will never ever be able to be replicated again. So out with the old and in with the new. And it's a photograph I'm incredibly proud of for our company because they're both sets of our equipment. So with that side done, we could then design and manufacture a striking mechanism because they wanted to make it so that Big Ben could sound for Remembrance Sunday and New Year's Eve and any other state occasion. So as you know, Big Ben has a unique sound, the bell. And the reason it has a unique sound is that it has a crack. And I didn't want to be the man who made that crack even worse. So what I decided to do was replicate exactly the same length of lifting cam, exactly the same length of arm, and therefore, if anything happened, I could say it's exactly the same. So we made that, and now with that in place, we could then start to look at dismantling the clock movement itself. The thing is, with the clock, the only way down was down the weight shaft. And the clock is sitting above the weight shaft. So you have to start to dismantle all the clock, and you end up piling 5.5 tons of clock around you as you're dismantling it. At the same time, you're having all different scaffold alterations because we had a scaffold so we could work to take the dial motion works. Then we had that removed so we could get to the clock movement. We started to dismantle the clock movement. We then were left with just the frame with the 3 barrels in there. Our striking barrel closest to us, the going train barrel in the middle, and the quarter train at the end there. So we then had another scaffold alteration, which allowed us to start to lift out the quarter barrel. Now, this quarter barrel with the famous Westminster chimes weighs 1,720 pounds. It is the largest horological component in the UK. So we had to lift those out, put them onto a wooden stand, which we'd already made, and that then allowed us to dismantle these, ready for us to take those down the tower. This left us with one last piece to get out the way, and that is the pendulum. Now, this pendulum is massive. It's 15 feet long, weighs 620 pounds. We also realized that the pendulum, the flooring and the casing around the pendulum was put in after they hung the pendulum, which just meant it was going to be a little bit tricky. So it meant we had to cut out parts of the floor. We then used that little clamp on the top is one of the originals. They use that so you can replace the suspension spring. We then stropped that up to a block and tackle. We ended up having to use 3 different blocks of tackles in 3 different places. We got it up so far, and then with a lot of manpower and grunt, and luckily without health and safety looking too closely, we managed to get the pendulum over the top of the clock frame and onto the floor. Now, the great thing about the Great Clock of Westminster is that Lord Grimthorpe, Edward Denison, wrote a book called Clock, Watches and Bells. And in 1860, a year after this clock had been installed, he did a revision of it. And in that revision, there was a large section about the Great Clock of Westminster. And that had all the details on how to dismantle the pendulum, which is really unique to be able to read a book written by the man who designed the clock that you are working on. And that proved really useful during the whole restoration process. So we got that out, and then that allowed us to start to think about getting these parts down the tower. There was one other problem in the way, was 10 feet of sandbags at the bottom of the tower. These had been there since year dot. They'd almost turned like concrete. So we had to get those out the way, and then that left us with just the 3 weights hanging in the bottom of the tower. Now, to give you an idea of this, the size of these, the going train weight, the smaller one, weighs 330 pounds. The quarter chiming weight at the back weighs 1,720 pounds. The one for the hour strike, to strike the mighty bell, weighs 2,680 pounds. That's like hanging a small car off your weight line. So once we got those weights out, they're in segments, so we could take those out. They were pretty damn heavy. Rolled them out of the tower. That allowed us to start to lower parts of the clock straight down the weight shaft. It's 175 feet down the weight shaft. So we had all those components you've seen stood around. It took us 2 days to get them out, including the pendulum, as you can see, just being taken out on the pallet truck there. The corridor there is where all our MPs run up and down, going to do their bits and bobs. No matter how hard we tried, we couldn't hit one. And we tried. Anyway, that just left us with the frame of the clock in place. Now, I'd really have liked to take this out. It's a wonderful, beautiful frame. But as some of you will know, and I'll talk about later, that in 1976 there was a disaster with the clock, and the quarter end, or the last third to the right, broke in half. And to repair that, they put in some substructure underneath, which goes into the tower wall. And I felt that if I disturbed that, I could open up a whole can of worms. So we decided to leave that frame there. We boxed it up, and we actually ended up restoring that on site. But all the other components we took away. They're all stored on site, and then we had to transport them secretly up to our workshops, which are just situated behind a 13th century castle up in the Lake District. It took 3 journeys to get them up there, because even though the clock mechanism itself weighs 5.5 tons, the whole installation, when you look at the hands, the motion works, the bevel gearing, the hammers which strike the bells, everything weighs in excess of 11.5 tons. So we transported that all the way up into the Lake District, and it was put into alarmed secure storage within our workshops. You may wonder why it had to be done in secret. I mean, there was a genuine concern that people would try to come and steal parts of the clock, or to damage it in such a way that it wouldn't be able to be returned to the tower. So we had to take great care. We were very secure. When the alarm went off, we'd have the police and the fire brigade there really quickly. It was quite interesting. So once we got it there, the first process we had to do was start to clean the clock. Now, there are 3 different types of cleaning. Just this basic first exercise of work, working your way through the clock mechanism. On the left, we've just got a normal degreasing tank. We use a thing called CitraClean. It's a really good, soft, degreasing fluid, which kind of gets rid of a lot of that kind of soft and dirty grease. On the top, we have a thing called an aquablast. The aquablast is a little bit more powerful. It has very, very small glass beads, like made out of almost like talcum powder. And this is in water, so it's cushioned, which is really good on kind of the steel work, the bright steel work and brass. It just gently cleans it. And then the third one at the bottom is a system called dry ice blasting. And dry ice blasting was something we came across through the Victoria and Albert Museum in the centre of London. It's dry ice fired at high pressure onto contaminated surfaces. And this causes little thermal shocks, which actually then blast the dirt out the way. And this was really, really useful on parts like that's one of the hour pipes for the clock mechanism, but also like the barrels, where you got all these years of grease which have been forced into the cast iron work. So we were able to kind of blast that away with that. So with the three different types of cleaning, we could start to get a headway into that 160-year-old dirt. We also had to start to look about how we could move these things around our workshops. I mean, they're big, they're heavy. You don't want to be kind of having four-man lifts all day long. So this is just one of a series of different carriages that we moved around. They all got numbered, Big Ben 1, 2, 3, 4, and 5. It was like Thunderbirds at the end. But we still have them and we still use them. They're very useful. So once we got all the components clean, the Parliament were very clear that they wanted this to be a very, very thorough examination of all the components of the Great Clock of Westminster, because they realised it was a its own lifetime opportunity to have this done. So we started doing on parts where we thought they could fail and could cause damage. We used dye penetration crack checking. So we put this on, we could then check with a UV light if there's any cracks or anything to be concerned about. And if there was, then we could repair it accordingly. And then we started to look at some of the repair work that we knew that was going to have to be done. And the reason for the scaffolding was to take the hands off. And it's mainly these rollers at the front of the hour pipe that were causing the concern. The minute rod runs all the way through the hour pipe, and those rollers you can see in the bronze casing support the end. Both the rollers had become worn, and so the minute rod, was dropping violently to one side as it started to rotate. And also, you can see where those rollers are, just that little furrow where the rollers had operated. And that little furrow, which is only about 1.5 millimeters deep, was taking away all the end shake in the minute rod. And you'd think on something so massive, it wouldn't have any effect. But it was quite surprising what extra pressure that put on the clock movement. So we had to address that. And then this is one of the sets of motion work put together in our workshop with all those minor repairs done. And the way we overcame that was we realized that the rollers had worn, so we knew we were going to have to make some new rollers. I didn't really want to just kind of metal spray 1.5 millimeters because I didn't know whether that would adhere well enough. So what we did is we machined down to the bottom of that wear and then made the rollers just that 1.5 millimeters more in diameter. And that put the minute rod back in the right place. So once we got the hands like this, we'd done all those repair works, but as a lot of you know, that you can repair your motion works, but the only way you can check them is by putting the hands on. When the hands belong to a 22.5 foot diameter dial, it's a little bit more complicated. So we built a scaffolding outside our workshops, and then we did one set at a time. We had to build the test frame on top of the scaffolding. We then hauled up each set of hands, put those on, put them in position, swung them round, made sure we were happy with them, and then took them all apart. It took about 1 week a set. And by the workshops, we have a public footpath where people walk their dogs. Not once did anybody come and ask us what we were doing. Anyway, it was very good training, as well as just making sure we had got all our repair work correct. It gave us the training in how to take the hands off and put them back on, something which proved very useful later on in the conservation project. We had some other repair work to make. This is the pinion on the hour striking train, on the fly arbor. And as you can see on the right hand is the original. And you can see the incremental wearing on the pinion. And this is just because as the pinion rotates, has to lift the hammer's heavier and heavier to lift, so you get that incremental wear. Made from cast iron, we had to make another one. We did this with die sinking, actually. We made a copper tool and we die sunk the teeth in because you could see that it's not an easy one to cut. And I didn't want to use dissimilar metals. Big Ben was quite famous because a majority of it, apart from one or two wheels in the going train, all the wheel work was cast iron. And so I had to make the new pinion out of cast iron. I couldn't test it until we got back to the tower. So just accurate measurements, and we made the new one. And thankfully, we put it in, and it worked perfectly. A very testing little project that. It doesn't look much when you look at it on a slide, but it caused me a few sleepless nights, I must say. And then these are the bevel gears, which are sitting underneath the clock on that fly arbor, which take the fly fans up above. They spin horizontally above the clock. The original ones were cast iron. They were replaced in about the 1980s with some bronze ones. But whoever made the originals, for whatever reason, used two different tooth forms on the bevel gear. I have no idea why they did that, but I kind of persuaded them that you should have the correct gearing engaging with each other, so we made two new sets. They're about 4.5 inches in diameter, made from bronze. So after we got that done, we were just really looking at some kind of straightforward, normal repair work that you find in any turret clock. Just some simple rebushing, some simple pivot polishing, and that went for, and as I said before, just that general tidying up of the repairs that had been undertaken by those other clockmakers who didn't have the time to do what they would consider would be a proper repair. So that gave us an opportunity to just tidy up them. We were then able to repaint and re-lacquer. Now, this is where the world of restoration and conservation has to blur into one. The reason we decided to repaint the clock mechanism back to its full colour scheme was, one of the reasons, surprisingly, was that people had been using engine oil on lubricating it. And that had reacted with the original paint, and a lot of the original paint had turned to almost like chewing gum. And that just scraped off. Also, we'd had to remove some of the original paint to do the crack detection. So those places would need repainting. So we took the decision to have paint samples done. We found that the frame was originally grey, and all the wheel work and lever work was bull's blood red. And any of the original paint work which we knew was original and safe and we didn't have to take off, we made a note of, covered with Paraloid B72, and then applied the new paint surface. So that meant in the future, if anybody wanted to do paint sampling to find some of the original paint, they knew precisely where it was and they could get to it. We then finished all the steel work with microcrystalline wax. And this was because we didn't want to use lacquer. Lacquer would crack and allow moisture in and start to corrode again. What we did with these, even those big barrels and big wheels, we just warmed them up and applied microcrystalline wax in several coats. Some of these pieces had 7 to 10 coats of microcrystalline wax. It works perfectly because once it's back on site, where that wax wears away, we can just replace as part of the service contract. So you're just always adding to it. We did the same with the nuts and the bolts and everything like that, because when you undo them, if they're lacquered, they would crack. But with microcrystalline wax, you can just add another layer. And by putting it on warm, it absorbs right into the pores of the cast iron and the metal, which gives, and we haven't had any problems with it since then. This then has allowed us, with all the parts finished, to start to reassemble. Now, we knew we wouldn't be able to test the strike and the quarter train because the frame was still on site, but we could test the going train. And so the first thing we did was Reassemble the Pendulum. It's a compensated pendulum, so it has the thin rod which runs the whole length of the pendulum. It has a plate at the bottom, or a nut at the bottom, and a washer, and from that springs a zinc tube. And then on the top of that zinc tube, the pendulum, or the outer tube which holds the pendulum bob, is suspended. So as the long, thin rod expands down, the zinc expands up, the outer part goes down, and it keeps the pendulum bob at the same height. Dent had been messing around with different types of zinc compensated pendulums, but this was the first one where he used the two inside one another, and it seems to work perfectly fine. So once we got the pendulum up and in position, we could then reassemble the going train. Now the front bar is original. That sits in the frame of the clock. The back bar we had to replicate, and we just made a piece of bar the same height as the front and then planted the train across that. We then made a split sprocket to fit round the barrel itself, and then that allowed us to put one of our automatic winding units on, and then we could start the clock ticking. And you'll see in the front edge, a front plane of it, just by the setting dial, 3 brass weights. And they're the original regulating weights that Dent used for regulating the clock. Not a penny in sight. But we'll talk about those later. And this is Lord Grimthorpe's double 3-legged gravity escapement. This escapement revolutionised public timekeeping in the UK. Lord Grimthorpe didn't believe in patents. So once he got this mechanism up and running in the great clock, and everybody realised how good it was, because it meant it didn't matter what force was being applied to the hand, the weather outside, the wind, the rain, it did not affect the impulse of the pendulum. It realised that you could keep these big clocks with large dials to accurate time. And so therefore, after 1860, you start to see all the other companies like Gillett and Johnson, William Potts of Leeds, all these other large public clock manufacturing companies in the UK starting to use them. During the whole project, we photographed every single item as it went through the workshop. So we got a set of photographs before we did anything, a set of photographs as we did all the different processes. We got over 3,000 photographs of clock parts of Big Ben. We also had to make a full set of engineering drawings for every component of Big Ben. The idea being that should a part of the clock break, then we'll be able to quickly use the drawings to make a new piece. And this, in turn, led us to be able to produce a set of renders, which look great. I love them. But what's really, really good for those is us being able to put them into a training manual, because they're so much easier to understand by just being able to explode components, say, lubricate here, don't lubricate there, use this type of lubrication here. And all those different things which you want to try to get across, because with any mechanism of this age, the knowledge of looking after it is passed down the generations of clockmakers. And sometimes it gets forgotten, little bits get forgotten. With a manual that we've been able to produce now, that information will not be lost again. You'll notice underneath, the green thing underneath, that is the first powered winding system built by Dents in 1913. And it never really worked properly since the 1950s. And part of our contract was to get that up and running. They had been using it by engaging everything by hand. But this had been designed to work automatically. Not come on automatically. You had to go up there, switch it on, and it would work and wind all 3 trains. And we'll touch back on how that works later. But the first thing we did is when we took that out, we had to reassemble it in our workshops so we could start to try to understand how it had worked. and the design of what dents we're trying to get to. So this is a frame we built in the bottom of our test frame. You could just see the pendulum bob of Big Ben swinging away there. We had a clearance of about an inch, luckily enough. I'd like to say I designed it that way, but anyway, so we kind of put it together like that and started to understand how it worked. And then we realized there was a part missing. And we're pretty sure we knew what that part looked like, but we weren't 100% sure. And so I went back to Parliament and I said, do you collect all the parts? Have you got all the parts of the clock? They said, yeah, we don't throw anything away. Everything's kept, everything's safe. We put it in storage, everything. I said, fine. They said, yep, we've got 6 boxes in storage in London, which will have all the components which have been removed from Big Ben in. I said, well, can I go and have a look at them? They said, yeah, no problem at all. Go down there on such and such a date and you can have a look at them. So I went there and I was greeted with this. It was like something out of an Indiana Jones film. So anyway, they took their 6 boxes down there, and in those 6 boxes were things like this. Now, these aren't all bits of clock. This is bits of any mechanical device I think they'd found on the estate and thrown into these boxes. But luckily enough, we found this bit, which we went rushing back with up into Cumbria. And lo and behold, it fitted. And we kind of knew what we were looking for, but it was just nice to get that reassurance. And it was quite amazing just to kind of actually find that piece and prove that we were right. And then that meant we could start to undertake the restoration works to this fantastic piece of engineering. And as I said, that we'll come to this again, and you will actually appreciate how clever the people were who designed this machine. So going back to the clock mechanism itself and the conservation work we're doing, we ended up having to do all the hammers. And this is the double hammer that strikes the lowest note on the quarter chimes. These hammers, again, like a lot of this clock, had never been taken out of the tower. They're made from wrought iron, all the bracketry is wrought iron, and the hammerheads are cast iron. A lot of the bolts and nuts were heavily corroded. A lot of the bearings were very badly worn. Again, it's not the fault of the people looking after it. They just weren't allowed to let the clock stop. So everything was just done quickly and whatever way they could. But this gave us an opportunity to start to take these back to how they would have been when installed by Lord Grimthorpe and his team back in 1859. Another part of the project was that we made the time capsule, which is now hidden at the top of the spire, ready for the next great project that comes along. Now, this is made from wrought iron sheet, which had been removed during the conservation program of the whole tower. In fact, this wrought iron sheet made a room which was suspended in the ventilation shaft. So they decided by using some of that, it showed that we're in the years of recycling. We painted half the tube blue, the other half black, to show from going from blue to black. And then inside there were put all the photographs and information about all the people who worked on the project whilst during those 5 years of conservation. So with that done, we started putting the mechanism back together. And the first thing we did was to put the dial motion works back in. And again, this is where you start to see how beautifully made the whole thing was. With the dial motion works back in, we were able to start to fit the hands back up. And now we knew the weight of these is a little bit easier to take them around the scaffolding. And once we got them in position and got them on the dials, we could appreciate for the first time what the dials would have looked like when first installed and painted with their original hands on, not the ones that we made. We did this to all 4 sets, and then we connected them back to the center set of bevels. And on the grey box there is another big synchronous electric drive we made as a company in 2007 when they're doing some other works to the clock. And that sits on top of the bevel gears and can drive all 4 dials at the same time. The part at the back is the crab winch, again described in Denison's book, and was used to bring all the components up the weight shaft when he installed it. So I thought I'd take the opportunity to show you this little time-lapse photography of the scaffold being removed from the dial. And if you watch carefully at 12 o'clock, you'll see the Great British Workforce run down the stairs on the left-hand side, have their cup of tea and come back up at 1 o'clock. But here we go. And this is the dial that overlooks the river. One of the, as you come across Westminster Bridge, you can see it. At least their boss would know how long it took them to do the job. And it was quite a massive moment in London when that dial was opened up for the first time and started to show, with the original hands-on and everything else, started to show the right time. So here we have back to the bells. Now we started to fit all the restored hammers back into place. What makes these hammers unique are the rubber buffers you can just see underneath the hammerhead there. No other clock I've ever worked on, no other clock made since ever used these rubber buffers. And again, it was something that Denison and Dents decided would be the best way of dealing with heavy hammers. It wasn't a massive success because in the cold winters they do freeze. And so if you're in London on a very cold day, the bells will be quieter than they are on a very warm day. But it gave us the opportunity to make sure that all those the adjustment rods work correctly. And then this is a picture of Ben itself, the 13.5-ton bell. And this is the second bell, really. The first bell was installed, didn't get up the tower. It was down in Parliament Green, and they used a 2 heavier hammerhead on it. It weighed 15.5 tons, and that's split in half. They made a second bell, winched it to the top of the tower, installed it, put a hammerhead on it, which was too heavy, and it cracked the bell. So they then left it there for a while, did a quarter of a turn, and you can just see a square hole on the right-hand side where they terminated the crack. And that is why Big Ben has that very, very unique tone. And whilst we're on to the subject of bells, during the restoration, sadly, Queen Elizabeth II died. And the tolling unit we designed was made just in case this happened as well. Because as part of her funeral, we had to toll the bell from when her funeral carriage left Buckingham Palace. As soon as the wheels moved, we had to start tolling the bell every minute. And at the same time, a field cannon would fire in Green Park. And we did that all the way until she got to the Palace of Westminster. She lay in state for 5 days, and then the bell at Westminster Abbey, just over the road, tolled 70 times to bring her to Westminster. After the funeral, we took over the tolling, and we tolled her all the way to Wellington's Arch, where she was then driven to Windsor Castle to be buried. And it was a great privilege to be involved in something as important as that, doing the official timing of the strikes of the bell as the funeral took place. And it was something I'll never forget in my life. Anyway, going back to the clock mechanism itself, once we got the hammers and the bells in place, we could get the clock movement, which you'd seen previously in our workshops. And here I've got a small video of the first moment we set it ticking, and you get the unique sound of Big Ben. And that was quite a unique moment for us, because the mechanism had been out of the tower for 2 years, and so it was the first time it'd come back, and it felt like the heartbeat of the nation was now back to where it belonged. And with that in position, we could start to bring the barrels back, and that's us lifting the newly restored quarter barrel back into place. And at Christmas 2021, the mechanism with the barrels was in, the going train was in, we'd fitted one of our automatic winding units, and the clock was ticking. That then allowed us to start to regulate the clock. And here we have the regulating shelf with those famous pennies on there, and also some of the original regulating weights. Now, I didn't realise how popular the pennies were. I wasn't a big fan. I'd have got rid of them. I like the idea of just going back to Denison's and Dent's original regulating weights. But I think if I'd have done that, I'd have been hung, because the story, the history of the pennies at Big Ben are so important. To add 1 penny to the weighting tray, the regulating tray, makes a difference of 2/5 of a second in 24 hours. The first mention of pennies being used in regulating the clocks came around 1930s. Denison was really clever with the regulating, because you've got a 2 seconds pendulum. If your clock is a second fast or a second slow, it's really hard to cap that. You can't stop the escapement for 1 second. It's impossible. You can't open it up for 1 second. It's impossible, because it's a 2 seconds pendulum. So he made a tray that weighed 4 pounds, and if you put it on top, if you move the little weights off, put that on top, it would gain 1 second in 15 minutes, which was a great way of, we use it to this day. If you want to lose a second, that tray there just slides off, and it's made so you can just almost just catch it as it swings towards you, and then just put it back on. At this moment in time, Andrew, who's a young chap who's joined the clock team, has got the clock keeping amazing time. And actually, I phoned him this afternoon, because I knew I was doing this talk. I thought I'd phone him and say, what was the error after the weekend? And he said it was 2/5 of a second out in 3 days, which is not bad for a mechanism made in 1859, 200 feet above London, with all the wind and all the rain. It's an incredibly accurate machine. Once we got that regulating, we could start to put the mechanism back together. And this is us putting the center arbor in, allowing us to connect it to the dials and disconnect it for the first time from the synchronous electric drive. With that done, and it being driven by the movement, we could fit the big massive fly fans on. And this is the one at the back is the striking fly fan. The one nearest to us was the quarters. Now, we had a bit of fun and games with these. Even though we'd given the architects the measurements of these fly fans, the strike one hit the lighting rail and also the fire sensor. So they had to move those. The quarter one hit the wall. Now, we hadn't moved the clock, but the plasterers had been very, very proud at making sure that the plaster was perfectly square to the tower, which was something obviously the Victorians didn't care about so much. And it meant, now there's no way we were going to kind of cut the plaster away to make the fly fan spin. So we ended up having to make the armature that the fans sit on about 20 millimeters shorter, and that allowed it to get round the wall. But it was one of those moments when you put it on, you kind of go, clunk, what's going on here? The walls moved. Anyway, during the restoration, we came across this wonderful set of photographs of when the last team who stripped and cleaned it on site in the 1930s. And I think it's a great photograph showing these the people from Dents, just posing for a photograph from a photographer. So you see that PPE and health and safety wasn't too pressing then. So we decided we'll do something similar in a more modern way. So now with the clock back together, we could start to test it. And this was before the automatic winding unit went back underneath. So we had to wind the trains by hand for the amount of time we wanted to test it. Now, here is a photograph, this is a photograph of an image in the Illustrated London News of men winding the Great Clock of Westminster. It took 2 men 4 hours to wind the clock. And it's really hard work. You can see they're stripped to the waist there to get the job done. So I thought, well, I'll have a go at this. And so here I am, thankfully not stripped to the chest, with myself and young Andrew winding the clock. To give you an idea of what's involved here, you have to turn the winding handle 120 times to put 1 lash of weight line on the barrel. You need 62.5 turns of weight line on that barrel to do 4 days' work. That means you have to turn the handle 7,500 times to fill the barrel. The worst thing, every quarter of an hour, your hard work is disappearing down the tower. And that takes a lot of energy and a lot of effort, and that leaves its marks. And when we cleared up the lino off the floor, which had been down there for decades, we found these footprints worn into the sandstone of the clockroom floor. And it's amazing, you can put your feet into those footprints, put your hand on the handle, and it's just the perfect position to wind the clock. It was one of my favourite bits of the whole project, was finding those. You really did feel like you were standing in the footprints of the people who went before you. You really, really did. So thankfully, Dents designed this machine. And this is that powered system we spoke about earlier. Fitted in 1913. But Dents offered it to Parliament in 1909, 50 years after the clock had been installed, on the understanding that they could have another 20 years service contract. And they were going to do that free of charge. It took them 4 years to design and build it. And when you work on it, you understand why it took 4 years. This is another render of it. And the whole idea of it was that it has to, 1 motor, winding 3 clutches, going to each of the trains, the strike, the quarters, and the going. But it has to disconnect and allow the weights back onto the clicks so that it can do the quarter chime and the hour strike and then re-engage. With the going train, it had to supply maintaining power whilst winding the weight, and then switch itself all off when the weights are at the top. And what I'm going to do is show you a video, and I'll explain how this machine works. It's the only way I think I could do it. Otherwise, it's almost impossible. So one of the things you have to notice is that wheel. We call it the shark's fin wheel, which is obvious why. And you have to take a note of the number on it. And then you've got the detent, which is at this moment is held up by a bit of chain. So I'll talk us through it. It takes about 4 minutes, this video. So Andrew comes along, drops it down. He knows it's in the 7 segment. Starts the motor. That puts a little pressure onto the winding drum. He then disengages that and he sets the cam barrel to the same number 7. There's a little Reassembling power spring in there which he winds. By lifting these arms, he engages the clutches and the strike and the 40. So now we have the motor driving reduction gears which are driving straight into the barrel. And there's one of the dogs. And those are the clicks clicking away. These are the weights going up the tower. The machine goes onto the worn, drops off, indexes, and at this point it disengages the drive clutch. This allows the reduction gears to run backwards, and you'll see the barrel run backwards onto the clicks. The weight is now off the driving dog, you can see. Drops off again, it engages, and it disengages the dog clutch. This then allows, at 1/4 the hour, for the clock to do its magic. Then it drops off again, it indexes, and it engages the clutch again, engages the dogs, and away it starts winding. So with the going train, this wheel with the segment put out of it, we just engaged that. You then engage a winding pinion. It may look a bit dangerous, but there are no moving parts near there. Then you lift the counterweight up, but similar as you've done before. It indexes, and now the going train starts to wind. And in there is a little epicyclic planetary box which produces the maintaining power to keep the power going to the escapement while the going train weight is moving up. Now at this stage, this is 12 o'clock. Both trains are being disconnected. The going train is what you can hear being wound. It winds the going train during wound. So that's the quarters gone. So now this is your hour strike. Sadly, the general public never gets to see all this. It runs at something like 115 decibels when you're up there with all the machinery. Now after the hour strike is finished, you'll see that all the winding units spring back into action, both the strike and the quarters, and all the weights start to wind up now. That's the going train one, it gets to a height, it knocks out. That's the strike one, it knocks out. And this you can just start to see the weight line coming up. It pushes it aside, that knocks it out. All the clutches are now knocked out. Everything drops back onto its clicks. That's it running back. Switch off the power. Pieces return. You take out the winding pinion. Hangs up the detent so it can't jam. and then sets the barrel to its neutral position. And now the clock is just ticking away. Now that machine was really hard to work out how it worked, even though it existed. For the people who designed it and made it, hats off. It's the most complicated mechanism I've ever dealt with in my turret clock career of 44 years. And it's one of the things I'm most proud of. It's an absolute wonderful machine. So what's to stop if one of these weights, this 202,700 odd pound weight, should fall? The sandbags are now gone, and instead they have these steel sheets with a kind of a honeycomb structure in between, and that will take up anything which, if the weights fall that 175 feet. I wouldn't like to test it, but I've been told that's what happens. So what does happen if something like that fails? Well, on the 5th of August 1976, it did. And this is the devastation. The fly fan failed, the weight plummeted, the weight line on the quarter train was slightly too short. It snatched it through that 1,720 pound barrel up into the air and 6 feet across the room. And this was the devastation it did to the clock. My old governor, when I was working in London, was the first person up there, followed by another chap called John Vernon. And they got the clock up and running within 12 hours. They put a jack underneath it. They went and got the gravity escapement down in the museum and fitted that back into position and had it up and running. There was a great debate then about what they should do. They were thinking of replacing it with an electric movement. But John Vernon, who I was very fortunate to be his apprentice for a short period of time, said that he could rebuild it if the company would back him and Parliament would back him. And within 10 months or something like that, he rebuilt the quarter train and got it back up and running and saved this wonderful machine from the scrapyard. And he never really got the recognition for that work that he did. After that failure, the National Physics Laboratory designed these brakes, and they engage with the winding wheel and they just trundle along at low speed. But should something give way quickly, the pinion gets up to speed, a ball bearing is thrown up, which engages a Wormand wheel, which brings two arms clamping onto the winding wheel, very similar to the inertia reels in a seat belt. They've been tested, they're beautifully made, and they will also stop devastation happening to the clock. And these are the dials, as you see them now. They're absolutely glorious, glorious things, finished in their Persian blue, with handmade glass, which had to come over from Germany. I think, I should know, I think there's 112 panes of glass per dial. That's what they thought there was. And then they found another 12 during the restoration. So I think it's 324. And they just look magnificent. I mean, if you've been to London recently and seen them, they really do pop. The incredible thing about them, one of the things I didn't realise until I started working on them, is they run so closely to the dial. They're not like turret clock hands, which kind of are quite a long way from the dial, which kind of gives a kind of a strange parallax. But these dials almost look like wristwatches. In fact, I've had one made with those dials on. And they're absolutely fantastic, fantastic things. Behind them now, we have a whole series of LED lights, which can be made to change the dials to any colour that they want. But what they do is they've replicated the gas lights of old. And it looks fantastic. And in this photograph, you can see the movement within the glass, which again makes them absolutely beautiful, beautiful things. so here we have it. This is the finished mechanism in place in the tower, with the winding unit again. Now we know exactly how it works. Using that winding system, you can wind the clock within 40 minutes. It's a lot easier than 4 hours. It keeps incredibly accurate time. The Palace Clock team have got it, to keep fantastic time. There's hardly any wear on it, as we found when we did it. It's 165 years old. It'll do another 165 years without any problems whatsoever. And it won't be the machine which stops. It'll be us losing the knowledge on how to look after the machine. That's the worrying part. And I think horological organisations like HSNY and the Antiquarian Horological Society, the British Horological Institute, are doing their best to make sure those skills stay alive in the world, because it's really important. I'd hate to see machines like this starting to disappear. And during the 5 years I was working there, I got to think of this as being a beacon to kind of heritage craft skills within the UK. There's so many different trades involved in it. Young people learning new skills. One of them, which is horology, and that's the reason we're here. And let's just make sure that keeps going. Thank you very much for listening to me.
Keith, thank you so much for such an important lecture. The work that you've done is truly important. It's great that you're able to share this with us. I'm going to open up the floor for Q&A. If you have a question, just raise your hand and I'll bring the mic to you.
Thank you. That was very enthralling. When you do a restoration like this, you have obviously the question whether you want to use new materials or old materials in different sections. I noticed that some of the bearings, I'm using bearings as a general thing, there are better materials than iron for some of the rotating surfaces or some of the surfaces that get rotated on. How do you decide to go back to using iron rather than newer materials that are more friction-free, that have longer lasting times?
A really good question. I mean, I think I'm caught behind this kind of restoration conservation. And if the materials have kind of done 165 years service, I kind of feel that it's paying homage to the clockmaker who made the clock in the first place by using his material. Now, not saying that that clockmaker wouldn't have used the modern materials if he had them now, but I just feel that this machine was made in a time which I think I would like to keep it built around those parameters that were used then. So that's the main reason I decided to use it, the same materials. Also, it takes away any guesswork. If I was to use a different product onto a cast iron wheel from 1859, I wouldn't be confident that it wouldn't cause a problem with dissimilar metals. So from a professional point of view, I had the confidence that if I used the same material, I wasn't going to cause any deterioration through that.
Thank you. All right, question up here.
So, such a great talk. Thank you. Can you say a little more about how you isolate the movement from the hands getting buffeted around by wind?
Right, so Lord Grimthorpe's gravity escapement is it's kind of a constant force escapement. You have two weighted arms which impulse the pendulum, and they're lifted up and then dropped onto the pendulum. With a deadbeat or a recoil, the force is being applied from the driving train to the pendulum. And so if you have wind blowing onto the hands, then that increased force or reduction of force will have a direct effect to the power going to the escapement. With Grimthorpe's escapement, you didn't. So it meant that it's just the weight of the two arms which are being lifted and dropped onto the pendulum which are giving the impulse, hence it's gravity giving the impulse to the pendulum. And that meant, in a way, the driving weight is detached from anything which is happening to the hands on the outside.
Thank you. Any questions on this side of the room? Okay, sorry. Over here, back here.
Thank you for the incredible lecture. I'm just curious, from a security perspective, what was it like working at Westminster? Did you have to go through like a security check every day? Were they up there in the tower watching what you guys were doing? What was that like?
Security in the palace is quite good anyway, so you're vetted with passes which then operate to kind of get into the building. So security was pretty hot. Kind of getting any vehicles in there was hard. You had to go and get them cleared somewhere else in London, and then you were given a route that you had to follow into the palace. And they, you know, if you were late, they'd want to know why. So you're quite heavily monitored in that way. But once you're in the palace and once all your tools and all your equipment have been brought in, it was fine. You know, it's like working in any other establishment, really.
Okay, question up here.
Thank you so much. Such a great lecture. How big was your team that was working on this? Like, how much manpower?
Well, the Cumbria Clock Company employs 24 people. And I think everybody at the Cumbria Clock Company had something to do just so they could be part of this wonderful opportunity of working on Big Ben. The on-site team was mainly myself and another chap called Mark Crangle. We did a lot of the work, working with the Palace Clock team of Ian, Hugh and Alex at the time. So there's a team of about 5 on site. The clock team also came up and worked with us up in Cumbria. But the whole workforce, the workshop workforce, worked on the project as well. When we were doing other kind of aspects of it, like restoring the cast iron clock frame, we had another team of 2 people in there. We had John and Rosie. So everybody kind of worked on it because you're not going to be given that opportunity. And you wanted to make sure that everybody kind of got a bit of the pie as such.
Thank you. Question up in the front.
Great talk, thank you. The fire at Notre Dame happened in April of 2019, like smack in the middle of the work you're doing conserving here. Was there any ripple effect on the folks available to do conservation work, maybe not at the Cumbria Clock Company, but on the tower itself during that time?
What you mean the Big Ben, the tower itself?
Yeah.
I mean, they were so careful with anything like that, hot works, anything which could cause a problem. They really did monitor all of that very, very carefully.
Thank you. Question up in the front.
Wonderful talk. How many people now care for it? Is there a team of people who?
Yeah, there's the 3 members at the palace who look after it, and we also go twice a month to service it as well. So we're still involved.
Thank you. Knowing the weather, the British weather, of course, you know, the wind, the rain and everything. But now that, you know, London is experiencing more heat, I was just curious as to how, you know, how is it affecting it? Was the conservation, you know, took care of that or?
No, I mean, the thing is, it's still a mechanical clock like it was in 1859. Mm-hmm. So when we do get some very hot weather, it does affect the clock. But because the Palace Clock team, especially Andrew, are there with their little pennies just adjusting the weights, they can almost predict what the clock is going to do.
Right.
They've got that regulating down to such a fine art that the rare British summers that we do have, they can accommodate and work out whether it's a 2-penny worth or a 3-penny worth.
Right, nice. Thank you, thank you.
There's somebody at the back, Caroline, who's over there.
Hello, thank you. I was curious to hear, you've mentioned a few times about the sort of blending of conservation restoration work, and I'm curious to hear about how approaching conservation science has informed your work, and specifically maybe touching on things like, I've been thinking about just you mentioned the dissimilar metals, and I was curious if that was like a galvanic corrosion consideration, and if humidity and condensation are like sort of all factors that I know are challenging to deal with in a conservation context.
A really good question. I mean, conservation restoration is a conversation we could have for hours, I think, and everybody would have a different opinion on it. And I felt like I had to blur the lines with this project. You have people expecting it to look like a brand new pin, and to a certain extent I can understand why that is. But at the same time, you don't want to destroy any of the originality of the clock. I think as I touched on earlier, the clock had suffered over the years, and so there was no protection. So the painting, which is the main one, and re-lacquering, which has the biggest impact, was kind of that decision was made up for me, really, because the clock had to have some protective coating. With using dissimilar metals, the galvanic stuff, that wasn't too much of a problem, because we'll just use the original materials as a previous question we discussed. You've also got to remember now, it's the most mollycoddled turret clock in the world, I would imagine. The environment up there is really good for anything, and it is monitored well. And at the same time, we have got a very strict service regime, which again helps. I mean, a lot of these items suffer because of neglect, and I can guarantee you that clock is not going to be neglected.
Thank you. One question here.
Thank you for the lecture. It's wonderful. The restoration of Big Ben, right in the middle of it, COVID broke out. And so I'm interested to know how that impacted the timing and also the methods that you may have had to take to kind of maintain safety and whatever else. You obviously can't fix this clock over Zoom, so.
That was a very interesting period, because when COVID first came, when we all had to kind of isolate, we were able to still continue working in our workshops. So the conservation works could continue based in our workshops, because we could keep the distances required and everything. With the Cumbria Clock Company, if people wanted to go home and isolated, that was fine. If they wanted to come to work, that was fine as well. When we got to site, its site was completely different. It was run by Sir Robert McAlpine, a big company in the UK, and they obviously had very strict regulations on how many people could be on site, and that did impact the work, and it did slow the work down. It made manual handling very hard, as you can imagine, and team lifting, but we got through it. There's a couple of photographs in that where we're all wearing masks. Again, it's very hard when you're lifting something heavy. Wearing a mask is kind of a bit of a struggle. But yeah, we got there. The most amazing side of the COVID thing was that it's the first time I could walk around Parliament Square in the middle of the road with no cars. And while I was doing the conservation works on site during COVID, I was staying in Camden Town, which is about an hour and 15 minutes walk from the Palace of Westminster. And I used to walk that, and you didn't have to worry about crossing the lights or anything like that. The roads were deserted. And you actually started to meet people, and it was like being in a little village again. So I think that was the positive side, if we can say there was. London was a completely different place.
Thank you so much. Any questions up here on the left?
Thank you for your lecture. I want to know, what is your prediction for the future of Big Ben?
My prediction for the future of Big Ben. Well, as long as we, as I said, as long as we have trained people and the clock tower is still there, it should be fine. I can't guarantee, with the way the world is, if the clock tower is going to be there in 160 years' time. But I think the clock now is kind of a little bit, people are a bit more aware of what it is. They are very interested. They're starting to use it in primary school education. We're just starting to kind of get young people interested in time. And we hope to use the clock and the pendulum as a method of inspiring young primary school children into engineering. And there's a whole program called Primary Engineer, which is starting in the UK, and Big Ben's going to be part of it. So it's nice to see this old Victorian machine having an impact on young people's lives, not to make them clockmakers, but to kind of give them an interest in time, in engineering, and they could be the future engineers, in the coming years. So, yeah, let's hope it stays an inspiration throughout the years.
Thank you. Love that answer. We're just going to take a few more questions, and then I'm sure Keith will stay behind and answer any more. So we have one back here. Oh. Did anyone here have a question? On this side.
Thank you very much for the lecture. Can you speak to the ongoing sustainment efforts? You said you're in there twice a month. What are you actually doing?
What we're doing is mainly a lot of it is just checking, lubricating certain areas. But it's just, seeing that we've had this big restoration, we just want to keep an eye on all those aspects of it. So we have one day a month where we look at the clock mechanism and all the gearing all the way around on the inside, and one day a month of just going up amongst the bells and the hammers to make sure everything's secure and in good condition there. And it's a joy to do, because it's that attention to detail, just making sure that nothing is changing, especially after such a massive project. And as I've already mentioned before, machines like this suffer because of neglect. And so now it's mainly that. We don't lubricate it every time, because you don't want to see a mechanism flooded with oil. But it's just that, making sure that everything's fine. When you're hauling 2.5 tons of cast iron 175 feet up in the air, there is a kind of a concern that you want to make sure that everything is proper.
All right, let's take one more question, if anyone has. Okay. If not, Keith, thank you so much again. You gave us a really new appreciation of Big Ben. We'll stick around for a while. Don't forget that we're off for summer, and we'll see you back in a few months.